Hi, I'm Josh, and today I'm going to tell you about our ITCS paper about sparsity lower bounds for probabilistic polynomials. This is joint work with Arkadev and with Ryan. So let me start with a one-side summary of what our paper is about, and in the rest of the talk, I'll define all the terms here, and I'll go into more detail about the motivation in our results. So this talk is about probabilistic polynomials, which are a powerful tool to represent Boolean functions. A lot of prior work, such as the work of Rozborov and Smolensky for AC0 circuit lower bounds, has studied and made use of degree lower bounds for probabilistic polynomials. But this work is motivated by studying, rather than the degree of these polynomials, their sparsity. So sparsity upper bounds have recently been used as the main technical tool in a lot of algorithms for important problems like the orthogonal vectors problem and the all pairs shortest paths problem. So studying these sparsities of probabilistic polynomials is important for trying to speed up these algorithms or understand the limitation of these algorithmic techniques. So in this paper, we prove sparsity lower bounds, which roughly show that there's no substantially better probabilistic polynomials for the functions that are relevant to these algorithmic problems. So if you want to speed up the best algorithms for these problems, you need to take a somewhat different approach. Okay, so let me start by telling you about polynomials that represent Boolean functions, which is the topic we're studying here. So let's let R be, throughout the talk, any ring. If you want, you can just focus on like a nice finite field like F2. But our results are quite general and should apply to many commutative rings. So okay, so let R be a ring and let P be an n-variable polynomial. Then we say that P represents a Boolean function f on n variables if for every input x, that's a 0, 1 input to all the n variables, the polynomial evaluated at x is equal to the function evaluated at x. So let me give a simple example. Let's say we're focusing on the AND function, which is supposed to be 1 if all the inputs are 1, but 0 if any of the inputs is 0. Then this simple polynomial that just takes the product of all n variables exactly represents the AND function. You can see if all the inputs are 1, it's a product of a bunch of 1s, which is 1. And if any of the variables are 0, then the whole product will be 0. So it correctly computes the AND function. Okay. So there's, in general, two ways that we'll focus on here for measuring how complicated a polynomial is. One is its degree. So, for example, this polynomial I just gave for the AND function has degree n. You can see the one monomial is a product of n variables, so it has degree n. And then the second measure, which we'll especially focus on here, is the sparsity, the number of non-zero monomials when you like expand out the polynomial and write it as a sum of monomials. So for example, this polynomial for AND actually has sparsity 1 because it just has a single monomial. So yeah, as I mentioned, there's been a lot of work studying the degrees of probabilistic polynomials and all sorts of other kinds of polynomial representations of Boolean functions. But sparsity is a bit less studied, and the goal of our work here is to make progress on understanding sparsity better. Okay, so I told you about polynomials just now for exactly representing Boolean functions, but what we really study here is probabilistic polynomials. So what is that? We say a probabilistic polynomial in n variables is a distribution P on polynomials. So it's not just a single polynomial, it's a distribution on polynomials now. So the degree and the sparsity of this distribution on polynomials are just the maximum over all the polynomials in the support of its degree and sparsity, respectively. And what does it mean for it to compute a Boolean function? Well, we say the error of a probabilistic polynomial for computing a Boolean function f is this quantity here. It's like the worst case error over all x's of how well the probabilistic polynomial computes the Boolean function. So it's the maximum over all Boolean inputs x of the probability when you draw a polynomial from the distribution that the polynomial you drew is not equal to the function on that input x. Okay, so it's really important here that this is like a worst case notion over inputs x. So for the and function, for example, there's only one input where you're supposed to output 1, and all the other inputs you're supposed to output 0. So if you are somehow, instead of a worst case over x, somehow considering like average case over x, it might suffice to use the always 0 polynomial, which has degree 0 and sparsity of 0. So it'll only be wrong on the and function on one input. But here, we don't want to consider trivial solutions like that for a variety of reasons. So we really want to focus on this worst case notion where we look at the maximum over all x. Okay, so let me give you an example of a probabilistic polynomial for the and function. And this is actually a polynomial construction that Rozborov and Smolensky used in their original work. Okay, so here's a probabilistic polynomial for and. I'll give it over f2, so like the integers mod 2. And here's a construction for error epsilon. We're first going to set d, this will end up being the degree of our polynomial, to be the ceiling of log 1 over epsilon. Then our distribution on polynomials is defined as follows. So to draw a polynomial from the distribution, you pick d independent uniformly random subsets, S1 through SD, subsets of 1 through n, and then you output this polynomial. So the polynomial on the n variables is the product from L equals 1 to D, so like the product over all the subsets of this sum here, 1 plus the sum of the indices in the set that we drew of 1 plus that variable. Okay, so let's check that this really is a probabilistic polynomial for and with error epsilon. Well, first of all, if the input is all ones, so that means and is supposed to output 1, well, actually, we can see that this polynomial, no matter what random subsets we drew, is always going to output 1 mod 2. Why is that? Well, this is a product of d things. Each is 1 plus a sum of some terms that are 1 plus an xi. If all the xi's are 1, this term in parentheses is always 2, which is 0 mod 2. So this whole sum will always be even. And when you add the 1 in front, it'll be a product of d different 1s. So it'll always output 1 for sure. Okay, by contrast, if x is any other input, so at least some of its variables are 0, then you can check that each of these sums, the sum of 1 plus xi for I in the random subset, is either 0 or 1 mod 2 with probability a half. You can see this by using the principle of deferred decisions. So if you imagine picking, like focusing on an I where xi is 0 and picking last whether or not to include I in the set S sub L, whether or not you include it in the set changes whether or not the whole sum will be even or odd. So the whole sum will be even or odd with probability a half. So the whole probability will output 0 unless all d of the 1/2 probabilities came up to output a 1. So if any of these sums ends up being 0, the final result will be 0. But with 2 to the minus d probability, they'll all output 1 and the polynomial will output 1 by mistake. So the whole polynomial will output 0 with probability 1 minus 2 to the minus d, which is at least 1 minus epsilon. Okay, so this is a probabilistic polynomial for and with error epsilon. And we can measure its complexity. So first of all, its degree, like we said, is d. It's just the product of d different degree 1 polynomials, which is log of 1 over epsilon. Its sparsity, well, you can see we're kind of multiplying together d different polynomials with order n terms. So it's like at most order n to the d. In general, you can actually prove a slightly better bound than this by taking advantage of the fact that polynomials for Boolean functions can be assumed to be multilinear without loss of generality. So if any variable is raised to a power bigger than 1, you can reduce that power to 1 without changing the value of the polynomial on any 0, 1 input. So you can actually say it's at most this sum of binomial coefficients, which is a little bit smaller for big D. In our case, actually, this improvement is not going to matter so much. Okay, so there we go. So the main question we study in this paper is whether or not it's possible to do better than that kind of classical Rozborov-Smolensky construction of a probabilistic polynomial for and. So a bit more precisely, the question we focus on is whether there's a probabilistic polynomial for and on n variables over any commutative ring. Like just now we were focusing on F2, but it could be over a different ring instead. It would be fine. Where we want to simultaneously have one in polynomial and n error, logarithmic degree, and polynomial and n sparsity. Okay? So you can, well, let's verify that using these constructions we've already seen, it's actually possible to achieve any two of these goals simultaneously, but we don't yet know how to do all three. So if you use the polynomial we just gave for error 1 in poly n, you can see it does have log n degree, but it has n to the log n sparsity. So the sparsity is too high. If you instead use that previous slide polynomial for constant error, it actually has constant degree and polynomial sparsity. But again, it has constant error, which is more than we wanted. And if you use the exact polynomial from earlier, it has no error and it has one sparsity, but of course it has n degree, which is much higher than we're aiming for. So the constructions we've seen can achieve any two of these criteria, but not all three simultaneously. Okay, why are we studying this question? Well, first, I think it's a natural question on its own right. These polynomials have found uses in a lot of different applications in algorithm design, in circuit complexity theory, and other areas. It's just a nice math question, I think. But it's particularly relevant to us because this polynomial for the AND function has important applications in algorithm design, and especially for designing algorithms for problems that are important in fine-grained complexity theory. So the main problem I want to tell you about, algorithmic problem, is the orthogonal vectors problem. So in this problem, you're given as input 2n vectors, x1 through xn and y1 through yn. These are 0, 1 vectors of length d. And the goal is to determine if there's a pair of them whose inner product is 0. And I really mean inner product over the integers, not like mod 2 or something. So in every coordinate, at least one of them has to have a 0 so that this inner product is equal to 0. Okay, so there's a straightforward algorithm for this problem that runs in time like n squared times d, where you just, for each pair of them, check if they're orthogonal. The best known algorithm in the interesting case when the dimension is like a constant times log n actually really critically makes use of the probabilistic polynomial for the AND function that we just talked about. And it ends up having this running time, n to the 2 minus 1 over order log c. So for any fixed constant c, this is actually a truly subquadratic time algorithm for the problem, but as c grows, it becomes a quadratic time algorithm. So there's a very prominent conjecture in fine-grained complexity theory called the OV conjecture, which asserts that you can't improve on this very much. It says that for every delta bigger than 0, there exists a c bigger than 1, such that when you're solving orthogonal vectors in dimension c log n, you require time n to the 2 minus delta. So the algorithm shows that, for every c, there's a delta such that you can achieve this running time. The conjecture says for every delta, there's a c such that you cannot get better than that kind of running time. This is really widely used in fine-grained complexity theory. Williams showed that the strong exponential time hypothesis actually implies this conjecture is true. And most implications of the strong exponential time hypothesis from the literature actually use the OV conjecture and don't go directly from strong ETH. Okay, so how are probabilistic polynomials used in this algorithm? I'm not going to tell you all the details, but the big picture idea is to study this Boolean function that corresponds to the orthogonal vectors problem. So the OV Boolean function for a c, I mean, we're thinking of c as a constant, but it can also depend on n. It's a function that takes in like the inputs to the OV problem. So it takes in 2n vectors of length c log n, and it outputs this Boolean function. It's an OR over all I and j of checking whether xi and yj are orthogonal. So it does that check by doing an AND over all the c log n coordinates and making sure either xi or yj has a 0 in that coordinate, which would mean they're orthogonal. Okay, so this is the Boolean function, which tests whether this is a yes or no input to the orthogonal vectors problem. And you can make a probabilistic polynomial for it, and in fact, the algorithm makes a probabilistic polynomial for it by replacing the and with the probabilistic polynomial we just talked about previously. This ends up giving a polynomial for constant error with sparsity n to the order log c. Okay. Uh, Notably, if you could improve this a bit, if you could improve it to some fixed polynomial sparsity n to the k for some constant k that's independent of c, and use it in the same way as their algorithmic approach, this would refute the orthogonal vectors conjecture. So here, even though we typically even earlier kind of bound the degree of a probabilistic polynomial, it's really the sparsity of the probabilistic polynomial for OVC that's important in the algorithm. It would actually be okay if it were a high degree probabilistic polynomial as long as it's a sparse one. On the other hand, when we're studying the and function, it's important to simultaneously talk about the degree and the sparsity. The reason is when we're turning the and function, the and polynomial into a polynomial for OV, replacing this and in the middle with a polynomial, you're plugging into it, all these polynomials of sparsity like 2. So it turns out each monomial will turn into a bunch of monomials that depends on the degree of that monomial. So you kind of need the degree and sparsity of the and polynomial to simultaneously be small in order to use it in this way to get a sparse polynomial for the OV function. And I'll just mention, actually the best algorithm for the all pair shortest paths problem also uses probabilistic polynomials for this same OV sub c function, although it's in a less direct way. Okay, so let me now tell you our main results. The first is that there is no probabilistic polynomial for and on n variables over any commutative ring R, which simultaneously has one in polynomial and n error, log n degree, and polynomial and n sparsity. So it's not possible to achieve these three conditions simultaneously. And this holds even if instead of thinking of like 1 as true and 0 as false, even if you pick any two elements of the ring and choose them to represent true and false. Okay, so in principle, this kind of change could impact especially the sparsity of the polynomial, as we'll talk about more in a second. But even if you make a change like this, there's still no polynomial for and that simultaneously achieves these three properties. So this rules out kind of using this approach to design a better probabilistic polynomial for the OV function. But you could wonder, maybe there's a way to make a better probabilistic polynomial for the OV function that doesn't make use of an and polynomial directly. It somehow makes a polynomial simultaneously for the whole function without specifically making a polynomial for and. But actually, our second main result shows that even this is not possible. So for every C, every epsilon, and every finite commutative ring that's not too big, it turns out this is a technical requirement for our proof, but probably not so important for the algorithms. Probabilistic polynomials with constant error for the OV sub C problem, which use the 0 of the ring to represent false, need sparsity n to the log C, like we achieved earlier. Okay, so just more generally for this OV sub C problem, you can't get a better probabilistic polynomial. There is one caveat here that for this second result, we really need the 0 of the ring to represent false. So let me talk a little bit more about this. So in all our examples we talked about earlier, we've been using the 0 of the ring to represent false and 1 to represent true. But you could imagine making other choices. And it's not so hard to see that other choices cannot change the probabilistic degree of a polynomial. You can like switch between choices without impacting the degree, but they can change the probabilistic sparsity. So for one concrete example, if you consider this complements function, which takes two bit strings x and y, and it computes the and over all the entries of, oh, sorry, this should be an I here, not a k, of whether of the parity of xi and yi. So if you look at this function, when you represent true and false by -1 and 1, then this function actually has a probabilistic polynomial of polynomial sparsity and inverse polynomial error. you actually can get it by plugging in the parities, which in this case are just a single monomial, into our and probabilistic polynomial from before. So it's really using the fact that when false and true are -1 and 1, this parity in the middle is a single monomial. By contrast, one corollary of our result is that if instead you represent false and true as 0 and 1, it's not possible to achieve polynomial sparsity and inverse polynomial error. So this is at least one example where this choice of what is false and what is true can make a big difference in the sparsity. So for the orthogonal vectors polynomial, there's not like a natural choice of basis other than 0 and 1 to use for that function, but we don't rule out that some other choice could get a better sparsity probabilistic polynomial. Okay, so let me mention really briefly some of our key proof techniques. I'm not really going to go into much proof detail. You can read the paper if you're interested in it. But the overall idea is that we actually use three pretty standard ideas from the complexity of Boolean functions and of polynomials for representing Boolean functions. But we kind of combine them and make use of them in novel ways. Okay, so the first is that we use some really careful random restrictions where you randomly carefully set some variables equal to fixed values. When you're doing random restrictions and focusing on sparsity, you can kind of separately focus on each monomial and calculate what's the probability that this monomial will be reduced or completely eliminated by setting a variable to 0. So if you have a small number of monomials and they're all of low degree, you can argue that or any of them are high degree, you can argue that random restrictions will impact them in a really fine-grained way and control how they'll impact the polynomial. The second is the short zipple lemma, which says that low degree polynomials must have many roots. And there's the function, the OR function, which comes up in these like the OV problem and is very related to the AND function. The OR function only has one root. So the short zipple lemma is kind of saying that low degree polynomials have to be very bad at computing the OR function. And this is a principle we make use of quite a bit. And a third tool we use is multi-party communication complexity. So it's kind of well known that if you have sparse and low degree polynomials, then you can use them to design efficient communication protocols where kind of the players work together to evaluate the polynomial and thus evaluate the function they're working on. So we make use of known communication lower bounds to give bounds on the sparsity and degrees of probabilistic polynomials as well. Okay, and let me finally mention, we have a few further results in our paper that I didn't talk about here. We have some sparsity lower bounds for other Boolean functions. We have some results giving formal relationships between probabilistic polynomials and some constant depth circuit models and these problems I talked about in fine-grained complexity theory. And we also talk about the relationship between probabilistic polynomial and something called probabilistic rank, which is a generalization that also suffices for these algorithms. So if you're interested in learning about these, you should check out the paper. Thanks.